Welcome to Mrs. Z's Chemistry. In this video, we'll learn how we can connect these concepts that we've been learning about the ideal gas law with stoichiometry. Remember that the coefficients in a balanced chemical reaction are the mole ratios between the reactants and the products. Moles is the goals is an easy way to remember that you must convert to moles before using the coefficients in a balanced chemical equation. So if you were given grams in the problem, you would need to convert to moles of that substance before using the mole ratio. However, moles is also a variable in the ideal gas law. So if you're given the pressure, temperature, and volume of a gas, you could solve for the moles using PVnRT, PV is equal to nRT, and then use that mole value in a stoichiometric calculation, which means use the mole ratios from the balanced chemical equation that you're given. So let's begin with this problem. How many grams of zinc are required to produce 2.4 liters of hydrogen gas at STP according to the chemical reaction below? We're asked for grams of zinc, but we've been given the volume of a sample of hydrogen gas. Because this problem is at STP, standard temperature and pressure, we could use the molar volume of gas as a unit conversion. So let's go to the periodic table and find the molar volume of gas at STP is 22.4 liters. So let's solve this. We have 2.4 liters of hydrogen gas. 22.4 liters of any gas at STP is 1 mole of that gas. So if we were to solve this, 2.4 divided by 22.4, we have 0.10714 moles of H2. But let's also solve this using PVnRT. So PV is equal to nRT. Rearranged to solve for moles is PV over RT. When we plug in our values, we have 1 atm for the standard pressure. The volume is 2.4 liters. That's what we're given here. The R value is 0.0821 liters, atmospheres, moles, and Kelvin. And then the temperature at STP is 273 Kelvin. When we multiply across the top, divide across the bottom, we get the same value. So that is why 22.4 liters is the molar volume of any gas at STP, because our pressure and temperature are these specific values. All right, so now we have to solve with stoichiometry. We have this amount of moles of hydrogen gas, which is this one in the chemical reaction, and we're trying to find out how many grams of zinc. So we're going to start out with the moles of hydrogen gas that we just calculated, and then use the mole ratio. The coefficient of hydrogen is a 1, the coefficient on zinc is a 1, and then we need to use the molar mass of zinc from the periodic table. Multiply across the top, divide across the bottom, and we come out with 7.0 grams of zinc as our answer. This problem is very similar to the previous problem, only it isn't at STP, so we can't use the molar volume. We have to use PVnRT, PV is equal to nRT, to find the moles of carbon dioxide. Pause to work this problem out. So here we use PVnRT, rearrange to solve for moles, plugging in our pressure, volume, R value, and temperature. And we've calculated 0.1410 moles of carbon dioxide. The mole ratio between carbon dioxide and calcium carbonate, the substance we are trying to find, is a 1-to-1 ratio. Then use the molar mass of calcium carbonate, which is 100.087. We come out with an answer of 14.1 grams of calcium carbonate. Pause to work this problem out. Again, first, use PVnRT to find moles of nitrogen. In the problem, we are given 36 liters is what we want the airbag to be filled with. The airbag is going to be filled with a gaseous product of the chemical reaction. The products are sodium solid and nitrogen gas. The nitrogen gas is what's going to fill the airbag to a volume of 36 liters. So that's why we want to produce 36 liters. So using the 36 liters of nitrogen, we can solve for moles of nitrogen. We have 1.686 moles of nitrogen. The chemical mole ratio is 3 to 2 between the nitrogen and the sodium nitrite, or NaN3. Then use the molar mass of the sodium azide, the NaN3, and we come out with 73.1 grams of the NaN3 is what we want to start with in order to produce 36 liters of nitrogen gas. Determine the volume of H2S at 425 Kelvin and 1.3 atmospheres needed to produce 65 grams of sulfur. Assume there is excess SO2 present. Saying that there is excess SO2 present means we have plenty of SO2 in order to react all of the H2S that we are trying to find. All right, the volume can be found from the ideal gas law. So let's rearrange. PV is equal to nRT. We don't have moles of H2S. In Pivnert, though, we have the R value, 0.0821. Liters, atmospheres, moles, and Kelvin. And then we have the temperature, which is 425 Kelvin. And then pressure is 1.3 atm. So in order to solve for the volume of H2S, we need the moles of H2S. So in this problem, we need to do stoichiometry first. So here we have our Pivnert all set up, just waiting for the moles of H2S to be able to plug into this and solve for the volume of H2S. So let's start with what we are given. We're given 65 grams of sulfur. The molar mass of sulfur from right here is 32.066 given from the periodic table, and that is that many grams per 1 mole of sulfur. Then the mole ratio is 3 moles of sulfur to 2 moles of H2S, which is right here the coefficient of 3 and the coefficient of 2. Then we can solve for 1.351 moles of H2S. Now we can use that value of moles right here into Pivnert in order to solve for the volume. So plugging in our 1.351 H2S times the R value times the temperature, divide by the pressure, and our answer is 36.3 liters of H2S.